Jeff, you are connecting?
Yes, I'm here now.
Okay.
Can you hear me now?
Yes.
Okay, very good. So welcome everybody to the panel on precise point positioning service. There's been a lot of advancements in this area recently. And so we're going to hear from some experts on this from different parts of the world and some of the things that are going on related to precise point positioning. So our first speaker will be Mr. Rui Hirokawa from Mitsubishi Electric Corporation. And he's going to be talking about the ICG and some of the things that are going on multilaterally related to precise point positioning.
Okay. Just the screen is available. I'm sharing my screen. Can you see my screen?
I can see your screen.
Okay. Thank you. Hello, everyone. Thank you for the introduction. Today I will introduce two topics. First one is the QZSS, which is a satellite-based open PPP-RTK service in Japan. The another one is a recent international activity for interoperability of PPP services. At first, I will introduce QZSS. It's a centimeter level augmentation service, which provide centimeter level accuracy position in a minute. QZSS is the first open satellite-based PPP-RTK service covering Japan. And the operational service was started in November 2018. So for now, it has been in operation for more than 4 years. The figure shows the structure system configuration of CLAS, which generates SSR correction in real time using coast station network in Japan. It includes error correction for signal in space errors such as orbit correction clock and signal bias. It also includes atmospheric correction such as ionospheric and troposphere. Next slide shows application of QZSS. It covers all wide variety of industry applications such as automobile applications such as ADAS, its automatic driving system, and agriculture, and automatic shipboard application such as automatic busing. And there are many drone application in the domain of delivery and agriculture. The next slide shows the typical performance of QZSS. It reached the centimeter accuracy in a minute. The left figure shows horizontal accuracy in more than 4 years operation. And the right figure shows convergence time. This figure shows 30, for example, 35 seconds in last December. It includes time to correction, time to receive the correction data. It's in the worst case estimated as 30 seconds. So 35 seconds is once we receive these correction data, it means it converges within 5 seconds. So it means almost instantaneous convergence capability. In the last summer season, the performance was somewhat degraded because of ionospheric delay is passing from north to south direction in Japan region. So we are continuously try to optimize our configuration in system. The next slide shows the typical performance of low-cost mass production commercially available PPP-RTK receiver, which means it's highly important availability of such as low-cost high-performance receiver. So currently, U-block F9P and D9C, as well as the septentrial mosaic CLAS, covering natively supporting our QZSS service. This figure shows a typical example of the performance for 1 day. So it proves 3.3 centimeter, 95%. It is a very excellent performance for PPP-RTK. Next figure shows ecosystem of our PPP-RTK service. The ecosystem for new kind of PPP-RTK system is highly important. We are providing open format specification named compact SSR, is compatible with LTCM. And we are also providing open data archive for analysis. And we're also providing reference implementation of PPP-RTK toolkit. And we are also supporting user by email. The next topic is introduction of our international activity for PPP interoperability. As you know, there are many kind of open satellite-based PPP or PPP-RTK service in this decade, and the low-cost receivers are also available in mass market. So we think open high precision GNSS portioning would become commodity in the middle of 2020. It is a good thing, but if many different service and manufacturers are available, the receiver manufacturers need to support wide variety of PPP service and application. It considerably increase the support and development effort for receiver manufacturers. So PPP Interoperability Task Force in the frame of United Nations ICG has established in 2019 to solve such issue. 3 co-chairs were elected from Europe, Australia, and Japan. Members of CPITF include wide variety of countries, which are providing PPP service or interested to support such service. And the CPITF has a main objective to improve interoperability of PPP service, which we already analyzed a key parameter of open PPP service, and we made a draft edition of PPP service provider report, which intended to be available in ICG website soon. We are also intended to have a recommendation of common terminology and algorithm. It's such as model will be discussed and defined as a standard recommendation. So this is the end of my presentation. Thank you very much.
Okay, thank you, Rui. So our next speaker will be Dr. Ignacio Fernandez. And Dr. Ignacio Hernandez is responsible for GNSS authentication and high accuracy service at DG DEFIS at the European Commission. From there, over the last decade, he proposed new features for Galileo, later known as Open Service Navigation Message Authentication and High Accuracy Service, and he coordinated their development. He's also co-chair of various international groups, including the European Union Authentication and High Accuracy Working Group and the ICG PPP Interoperability Task Force. In 2017, he was a visiting scholar at Stanford University GPS Lab, and since 2020, he is a visiting professor at QU Leuven, where he teaches GNSS. Earlier in his career, he worked in industry for 6 years as EGNOS system validation engineer and system test manager, among other assignments. He's an engineer from ICAI Madrid and has a PhD degree in electronic systems from Aalborg University. So please welcome Dr. Hernandez.
Hello, everybody. Good morning, good afternoon. Can you hear me? Can you also see my presentation? Thank you. Thanks very much, Jeff, for the introduction, especially for your effort in spelling out or saying well the acronyms, which is not easy. So I have been in charge of the Galileo High Accuracy Service for the last years at the European Commission. We can happily say that we declared the initial service right 1 week from today, on Tuesday last week. So now the Galileo High Accuracy Service is operational in its initial capability, and we are very excited about that. So I'm going to present briefly some information on the Galileo High Accuracy Service, including the current performance and the next plans. So first, why we are doing Galileo High Accuracy Service, then what it is, then, as I said, the performance, and then what comes next. So why are we doing Galileo High Accuracy Service? First of all, Galileo foresaw an added value service called commercial service at the beginning of its definition from the very beginning, but this service was going to be offered at a fee. But in March 2018, the EU as a whole decided to offer it for free with a target 20 centimeter accuracy. But a question we need to answer is why we are doing that. There were reasons not to do that, which were mainly the already existing ecosystem of commercial providers that were providing already high accuracy services. But the first reason was we believed it follows a natural trend in accuracy, starting with the GPS operational declaration in the 90s, still with selective availability, continuing with the removal in the 2000s of the selective availability, continuing also with the appearance of new GNSS, providing more satellites, more signals, more frequencies, and also improving accuracy. And then continuing with the next step that we are taking now, as my colleague Dr. Hirokawa said before, which is the provision of high accuracy services, PPP or RTK, as a commodity, which is what we are starting to observe and we will continue observing in this decade. So Galileo HAS follows a natural trend. It is also part of an ecosystem in the sense that it provides high accuracy, but it is not the only one. So the level of disruption is limited. Yet we believe it's a first of its kind in the sense that it provides global coverage. Excuse me. It is a free service and it is operated 24/7 with a warranty, and it is also standalone. So if we compare it to other services, for example, commercial ones, they may be also global, including the internet distribution, but they are not offered for free. There are regional services like QZSS, we just saw the excellent performance that it is providing already, but they are provided on a regional basis. And then there are other services that are global and free, like the excellent also IGS real-time service, but it is operated on a voluntary basis and therefore without warranty. So we believe we are a first of our kind to some extent. We also understand that there is a user demand to obtain high accuracy corrections. The demand is clear, but in particular, in the case of HAS, we believe it satisfies the demand of providing these corrections everywhere in the world, even in areas without connectivity, which, by the way, are still the majority of the area in the world. We also understand that while we are providing services that were provided commercially some years ago, we are leaving room for innovation at user and application and receiver level. In particular, we are not providing a level of accuracy comparable to other applications that are in the centimeter or even millimeter level. And then there are several user technologies that we cannot provide, like providing user integrity, which depends on the development of algorithms at user level, bounding or mitigating the local error sources. And finally, we are providing it with the existing Galileo infrastructures. For the EU taxpayers, this is a very cheap functionality that we estimate in the order of below 1% of the total budget of Galileo so far. So what is Galileo High Accuracy Service? Is basically our service to provide precise corrections, in particular corrections for satellite orbits, clocks, and signal biases. At the moment, we are providing code biases for Galileo frequencies and also GPS frequencies, not yet carrier phase biases, although it is in the specification, but we are analyzing it further to ensure that we can provide corrections for
I think Ignacio has a connection issue, I believe.
Yeah, it appears that we've lost Ignacio. So maybe we can come back to him if he can get reconnected here. But in the interest of time, we could move on to our next speaker, which is Ms. Yoko Sakai, who works for the Japan Cabinet Office and has been involved in MADOCA development and user expansion since April of 2022. So over to you, Yoko.
Hi, thank you. But I think main room was muted. Is muted.
Okay. I can hear you.
Can you hear my voice, online people?
Yeah, I can hear your. I can hear
Thank
your
you.
voice.
So how to share my screen? Okay, thank you. Okay, I am Yoko Sakai from QZSS Strategy Office, National Space Policy Secretariat, Cabinet Office, Government of Japan. And as you may know, QZSS provides MADOCA-PPP and CLAS as PPP service. And CLAS was introduced by Hirokawa-san, Rui Hirokawa. So I will introduce about MADOCA mainly. Okay. So these are the figures of ground tracks for current QZSS constellation and future 7 constellation. And QZSS system provides GNSS augmentation service, SLAS and CLAS for domestic, and MADOCA-PPP for Asia and Pacific region, where the QZSS can see. And SLAS is submeter level augmentation service, and CLAS is centimeter level augmentation service. And here are the overview of MADOCA-PPP. So MADOCA-PPP is Multi-GNSS advanced orbit and clock augmentation precise point positioning. And it began its trial service 4 months ago. And for the stable operation of MADOCA-PPP, Cabinet Office developed Mirai, a GNSS monitoring station network, and which is released in April last year. And also we are developing ionospheric correction function to reduce the initial convergence time. So we are looking for the opportunity of demonstration in cooperation with partners in Asia Oceania region to promote technical understanding of MADOCA and to consider feasibility to apply MADOCA to the user applications, and also to ask collaboration to provide local cores for ionospheric correction function. And here are the specification. You can download the specification document in QZSS website, and the ICD for ionospheric correction data will be updated next April. So today I'd like to supplement one point about the initial convergence time. So the initial convergence time is a little bit difficult to define, and maybe the definition of this may be different from each service. And the Cabinet Office defines it the time for 95% errors to drop below 30 centimeter in horizontal and 50 centimeter in vertical with condition of open sky and using dual frequency receivers for surveying. And here are the specification. And next, I will introduce about the example of actual performance during trial service. So here is one of the PPP results based on data from IZS monitoring station in Malaysia, in Asia. And the green line shows the 95 percentile errors, and during one month in December, last December. And you can see the initial convergence time is was 780 seconds, so which is shorter, which is smaller than the specification. And also after convergence, the horizontal accuracy and the vertical accuracy, which is 95% dial errors, are below 6 centimeter and 10 centimeter respectively. So this is the current performance of MADOCA. And the next, I will introduce about some demonstration cases using MADOCA. The experimental signal of MADOCA was transmitted from QZSS until the start of MADOCA's trial service. And in cooperation with private sectors and relevant ministries and agencies, the following demonstration projects were conducted. So such as autonomous driving of tractors, EVs, and drone for herbicide applications and plant observation, and soil volume measurement, and road surface provision service, mapping, and so on. And this is just the demonstration, but Cabinet Office would like to continue to encourage the practical application through demonstration projects with trial service as well. And also I will introduce some application using CLAS and SLAS, the augmentation service for Japanese domestic service. And I believe that MADOCA can be used for some application using CLAS and SLAS, especially the application of maritime. So now Japanese company announced the launch of the autonomous navigation vessels, and CLAS is used for autonomous vessel navigation and berthing. And the other example is buoys for real-time oceanographic observation. So this buoys uses CLAS to observe XYZ and uses AI to estimate wave heights and flow directions in real time. And this system contributes to improving fishery efficiency and prevention of maritime accidents. And the last example is artificial fishing reefs construction on seabed. So since RTK was not available offshore, where the construction site was located, CLAS can provide high accuracy positioning of vessels. Okay, I believe these three examples can be used for this example. And finally, a little promotion. I have two little promotion, but the first is Mirai. And Mirai is the system to gather GNSS data and provide real-time and archive data to users registered. And the GNSS data is kindly provided with cooperation of international and national institutions and university and so on. So I thank to such partners and also welcome cooperation from anyone interested. Okay, and one more, I don't have slide, but one more promotion. After this session, the MADOCA-PPP demonstration will be conducted in front of the entrance. So I hope you come and enjoy it. Thank you. That's all of my presentation.
Okay, thank you, Yoko. Very good presentation. So I will, before we move on, let's check to see whether Ignacio is back.
Yes, I am, and I really apologize for the connection. The connection was stopped apparently halfway. I'm really sorry. So I can continue whenever is suitable for the session.
Yes, why don't you go ahead and continue now, and apologies for moving on to the next person while you were getting your video fixed.
Okay, thank you very much, Jeff. So I will continue projecting, right? So I understood from my colleague Dominic Hayes that the connection was stopped in the middle of this slide where I was describing Galileo high accuracy service. So essentially, this is our PPP service provided through the signal in space and through the internet, and providing almost global coverage, almost because we cannot guarantee global coverage at the moment. We are in an initial service, but we hope we can do soon. This is the performance of standard point positioning without HAS, and this is the performance with HAS, which is in the order of 10 centimeters, as per the test that we ran in JRC, the Joint Research Center of the European Commission at ISPRA in September 2022. This is our network of monitoring stations, 14 plus 1, because we have 14 at the moment, and the 15th one is being integrated in the operational chain, which is the one in Wallis on the right. The data arrives to the high accuracy data generator, or HADG, which calculates the orbit, clock, and bias corrections and sends them to the ground control centers of Galileo in Germany and Italy. That send this information to our uplink stations. We have 5 of them worldwide with 4 antennas each that can transmit the information to our satellites, up to 20 satellites in a few seconds, and this information is broadcasted worldwide. On the left, you can see the apportionment of tasks between the main public contributors to the HAS, which are the European Commission, USPA, and ESA. This is the current coverage or service area as defined in the SDD, Service Definition Document. Unfortunately, we are not yet global, but the reality is that even in the area that is highlighted in blue, the service is receivable and with good performance. Just the performance is slightly degraded with respect to other areas, especially Europe. In this slide, you can see the performance at different stations worldwide. And in particular, you can see that the one closer to the Asia, to the East Asia region, while slightly degraded, it still offers decimeter level accuracy. So regarding the next steps, we are now in the what we call phase 1, which is initial service. This is what we just declared last week. And we expect to move gradually over the next years toward the full service. In the meantime, now that we have the service available, we expect that there will be more HAS-enabled receivers gradually in the market. My colleague, Dr. Hirokawa, already presented some chips that are QZSS and therefore E6 enabled. We hope that soon they will implement Galileo HAS as well. We have also some R&D projects to improve some aspects, both at user level and at infrastructure level of the HAS. And we expect in the next months to publish a HAS reference algorithm, which is the one that we will use as a baseline to, and that we have used actually as a baseline to validate our performance. We expect that the development of applications will continue. Another step that we expect to take in the next months is to provide phase biases. I said before, I don't know if it was caught, that we are providing code biases at the moment, not yet phase biases. So the performance I showed is with code biases only. Another feature we will add soon is authentication of the high accuracy service. With Galileo, we are providing authentication through OSNMA, but the HAS message is not yet authenticated. We expect to do it soon. And also some characterization of the errors for the users to be able to add this information to their computation of integrity and reliability. We expect to have more stations soon and to not only provide, but also guarantee global coverage and provide a better accuracy than the one we are providing now. And finally, as part of the full service, we expect to provide an ionospheric message over the European coverage area. So basically the European continent to speed up convergence, as for example, our colleagues from CLAS are doing. On the bottom, you can see the different service levels we have for Galileo. Service level 1 is what we intend to offer globally with a committed accuracy horizontally of 20 centimeters, 95%. And the service level 2, which is similar but with a shorter convergence time thanks to the ionospheric message over Europe. So this concludes my presentation. This is a collage of many of the people that participated to the Galileo High Accuracy Service, which is a collective effort of many teams in industry, in the public sector, in many places in Europe. I would like to thank all of them, and that concludes my presentation. Thank you very much.
Okay, thank you, Ignacio. Very nice presentation. So we will move on to our next speaker, Mr. Simon Reynolds. Simon is the engineering manager for the SouthPAN project at Geoscience Australia. He's worked as an engineer on aviation communications, navigation, and surveillance systems since 2011, notably on the generational transition from terrestrial radio systems to satellite-enabled technologies. Simon has worked on several safety-critical systems, including air traffic control computer systems, the ground-based augmentation system at Sydney Airport, and various aeronautical information systems. Simon represents Australia at the UN International Civil Aviation Organization and UN International Committee on GNSS on matters of standardization, interoperability, and coordination of satellite navigation services. So please welcome Simon.
Thank you, Jeff. Can you hear me okay and see the presentation?
I can hear you online.
Great. So thank you for the opportunity to speak today. Sawasdee Krub, good afternoon, good day to everyone. I'll just go through our new SouthPAN precise point positioning service, some of its characteristics, and some information that might be useful. So we've got 3 services are currently available in Australia and New Zealand today. So we started transmitting our first signal on the 26th of September last year. So it's in contrast to the Japanese and European services. These are quite new. Just touching on the SBAS services, we've got a L1 SBAS open service that augments the GPS L1 CA signal, and that provides accuracies of better than 3 meters horizontally and 4 meters vertically. We've got a dual frequency multi-constellation SBAS open service, which augments GPS on L1, CA, and L5, and also the Galileo E1 and E5A signals. And that achieves better than a 1.5 meter accuracy horizontally and 2.5 vertically. But of course, the one I'm here to talk to about today is the precise point positioning via SouthPAN, which augments the same signals as the DFMC SBAS open service, but achieves, users can achieve better accuracies at about 40 centimeters horizontal and 50 centimeters vertically with an 80-minute convergence. There's a lot more information about these services in the service definition document for open services, which we published with the commencement of services. And there are links at the bottom of the slide there. I encourage anyone who is interested in the technical detail of those services to have a look at those documents. There's a better link at the end of the presentation if you don't have access to this presentation. Safety of life services are in development, so they're expected to be commissioned in 2028, and they'll be available for use by aircraft. That'll just be the L1 SBAS signal at the moment, not the DFMC SBAS. So these are the service coverage areas where we guarantee our service availability. So the light blue area is where L1 SBAS is available, and DFMC and the PPP via SouthPAN is available in the dotted area that encircles both Australia and New Zealand. Outside of these areas, there is still benefit to using SouthPAN. However, the accuracy and convergence times might drop off as you get outside those areas there. Now that our precise point positioning service is currently delivered using the L5 navigation signal. So they're messages that are embedded along with the dual frequency multi-constellation SBAS standard messages. This is a solution that will continue through to about 2027, when we will have a new navigation signal. So the current PPP service will be transitioned from L5 to a new navigation signal. And with that transition, there will be improved performance. So the current L5 navigation signal is somewhat limited in terms of bandwidth, which means the users won't be able to achieve accuracies that will be achievable in the future. So the new navigation signal will be around the center frequency of 1207.14 megs. So it's the same center frequency as the European E5B signal and the Chinese B2B signal, and that will happen in late 2027. At that stage, the performance will improve from about 40 and 50 horizontal vertical to about 15 and 20 centimeters, and also there'll be an improvement to the convergence time. So we're providing these early services on L5 so that users that are out there today can derive some benefit from it. And you saw a lot of the use cases described in other presentations. There's transport, there's automotive, there's asset management. The list is endless. And the signals that are out there today provide the capability to users today. We'll provide more details of the transition from L5 to the new navigation signal, provisionally called L5B, at a later stage, as soon as we can, because we know that users will need sufficient time to build that transition into their user devices. But any receiver with that can receive L1 and L5, the whole band, will be able to use this service in the future. In terms of our performance so far, so the performance standard from the service definition document is in the top left there. They were the numbers from the first slide. We're achieving much better accuracy than our commitment. So this is only a 4-month average. We haven't been going for very long, but the numbers are fairly indicative. 16.5 centimeters against the performance target of 37, and then 25 centimeters vertically against 52. So it's roughly a 50% improvement on our commitment. The convergence time is just under 80 minutes, so not as fast as some of the others out there. Again, that's currently limited by the signal bandwidth for L5, and that'll come down with the new navigation signal. Our service availability is over 99%, so exceeding the 95% service availability promise. There was one of the previous slides talked about convergence, and we determine the solution is converged when both the vertical and the horizontal accuracy requirements are met. And then we measure that time, and that's a 95% confidence interval on the commitment. And we assume some things about the user algorithm. We assume it's basic, so real world performance from receivers with better algorithms than what we assume will get better results than the numbers presented here. But we assume a simple tropo model, iono-free combination, and a float solution. So most users should receive better performance than what we publish here. There's some further information on the program and the other services if you're interested on our websites. So it's a joint Australia-New Zealand project, and there are both Australia and New Zealand contact details there. The service definition documents are available on both those websites. And there's also a fact sheet for users and equipment manufacturers to incorporate SouthPAN services into their receivers or integrated systems. So again, thank you for the opportunity to speak today, and that's the end of my presentation.
Okay, thank you very much, Simon. And we'll go on to our last speaker now, Mr. Rod McLeod. Rod has a master's degree specializing in GPS from the University of New South Wales and 35 years in the GNSS industry. He currently manages the Asia Pacific region for the Autonomy and Positioning Division of Hexagon. This includes Novotel, which is headquartered in Calgary and is a world leader in GNSS-based high precision positioning solutions and correction services. Rod also serves on the advisory board for the Australian government to help develop a national positioning infrastructure policy. So welcome, Rod.
Thanks, Jeff. Can I have the slides, please? Okay. So I'm going to come from the commercial side of the business. So this is primarily looking at two areas. One is the established known PPP services globally, and what seems to be emerging is the enterprise solutions, which kind of work within industries where they want to control their solution in, say, a regional manner. So these are our traditional Hexagon positioning PPP services. The TerraStar and RTK Assist, which means helping RTK when you lose it. Global coverage, the first three. So marine services as well, oceanics, that's also global coverage. And the oil and gas industry, which, as I said earlier, has been working in the PPP space since the early 90s. Again, critical infrastructure needs positioning really accurately anywhere in the world. So this is typically, for us, we transmit the corrections on a frequency just off L1. We transmit on geostationaries over the equator, so that would be basically Inmarsat. And that's been this industry for a while, but there's been improvements made, and I'll show you that in a minute. And the other side I'll talk a little bit about is the TerraStar X Enterprise, which is effectively what most in the, where you're looking at agnostic receiver, doesn't matter. The first three, we control the whole infrastructure. We have like the whole ecosystem. So we know the base stations, we have redundant control centers, uplinks, and we also control the algorithm in the receiver at the other end. Okay. So if you look at that first side, which is the green side, that's the traditional market, and it's basically a business to customer or consumer relationship. So the customer buys the equipment and then gets the service. We typically used to see 15 to 18 minutes convergence. We now can converge anywhere in the world globally in around about 3 minutes. I'll explain how we do that. It's traditionally only on our receivers and our partners' receivers. The emerging market side is kind of where it's the PPP discussion is now moving. And that's, for us anyway, in the commercial space, looking for a business-to-business relationship, and where the other partner will then deliver to their customers, if you like, okay? It's going to be more regional, and it's probably looking at an accuracy at the lane level discussions as being talked about here now. There's also another problem in the sense that there's a whole bunch of requirements for delivery of format, and we chose the 3GPP solution as being the open format, or some customers want us to do proprietary. And then you're left with one big problem, of course, again, is in the each industry has their own standards when it comes to things like ASIL, so that's effectively an engineering standard for products. ISO 26262, which has been driven in the automotive industry, and each of them want integrity as well. So we call the improvement in the traditional market called RTK from the sky. It does two things. One, it makes a faster convergence to centimeters. It's global. But the really other good trick is it also means for most users that you have an instant reconvergence if you lose the signal. There's no discussion so far in any of the papers or in the presentations here about the accuracy after you lose it and get it back again. So how did we improve the old model? So the previous global performance was around about the 15-minute mark to get to 5 centimeters, if you like, right? What we did was we changed, or we looked at the ecosystem and we added extra signals. We did some end-to-end improvements and we noticed a huge accuracy improvement. And as you can see, it's gone from about 15 minutes down to around 3 minutes. Now, for most people, that in an industry, in a high precision industry, is enough. There's no need to go even further, say, to reduce it to a minute. 3 minutes is more than adequate. Okay. And so in a global sense, it's already covered for precise users. How do we do it? Well, what we did was we added all the new signals that are available in the sky. So now what we've done is we've gone to actually four constellations and 4 frequencies. And the game changer was effectively L5 was 1, but then if I could use E6 and B3, which we have, and the rollout of those signals is now coming to space, including for both Beidou and Galileo. It now means we can get this type of performance. And this is an example of using some of our stations. Remember, I said we own the whole ecosystem, so we have our own about 80 to 100 stations around the world we use. And as you can see, just using those stations and doing the algorithm old way and the new way, we have a huge 60% improvement. And the other thing that is really important is in the true user environment, they're not staying still, they're moving. They have to basically be able to handle losses of lock, going through a tunnel, going through trees, buildings. So if you look at the diagram, well, this is a typical urban environment in North America. If you look at the light green, that was the original mathematics of our convergence. And we found that if we stayed loss of lock too long, then the convergence never came back. Now, with the new solution, we can reconverge in pretty well instantaneously back to centimeters after a loss. Very important for users. So let's talk a little bit about the enterprise side of the business. So we in Hexagon are looking at primarily the on-road requirement of autonomy, which is effectively lane level navigation, because there are other sensors that help you with holding your autonomy in other areas. Other autonomous vehicles, off-road, including, say, tractors. You could do it also with robots, drones. And then the last one is the smartphone market, where this is mobile apps, Uber, etc., who want to basically know which side of the street you're on now, etc., games, reality, etc. So to do that, you have to look at increasing your hardware. Now, we're going to use third party, so anybody's hardware, and in the automotive and the mobile phone market, dual frequency receivers reception is just coming into play, L1, L5. Google Pixel, for example, offers carrier phase measurements, which you can apply in a mathematical model. So by using multi-frequency and multi-constellation, you can get down to around a meter. That's still not good enough. Then you add your correction service, so you can get to your decimeter with low-cost equipment, like GNSS. But then you need to do the advanced mathematics, and importantly, you have to have integrity. So traditional lane, GPS, if you're using it in your car now, is 5 meters really, 15 depending, and your map matching. But to get to the requirement for autonomy, you need dual frequency GNSS with proper correction services, with the ASIL standard, safety critical. So you have to have your corrections in a safety critical mode that will meet that requirement. So what we're proposing to our customers, and we just announced our first agreement with a company called ZF in Europe, who are automotive tier 1, who provide automated or electronic services and subsystems to the European automotive market. So we can give them effectively the performance they need on whatever chipset they want to use. We give them functional safety by providing them with a algorithm, PPP algorithm that will work with the functional safety requirements. And we can deliver it in a business model that they wish to have. In their case, they will take our data and then distribute it their way. So this is typically what you see now as the emerging market for PPP. So we have a number of test beds in this TerraStar-X solution. Remember, the global solution is already there, but this is for using anybody's hardware and basically testing mostly for the automotive market. And as you can see, it's in Europe, in North America, and in China as well. And we will be announcing some work being done in Korea and Japan this year as well. So the takeaway for the new part of the business is that you need to be compliant to the standards. In the case of the automotive, it's ASIL standards. And high precision is not just the chipset or the algorithm, it's a combination of everything together. Thank you very much.
Okay, thank you, Rod. Very insightful presentation. So I don't know if we have a couple of minutes maybe for some questions before. I know we have to break pretty soon, but we can maybe just take one or two questions if that's okay. And I just want to say that that we were very pleased to have all three of the ICG PPP task force co-chairs with us today to present. So you heard from all three of them, Ignacio, Rui, and Simon. So I just want to ask a question for the three of you, if you could maybe just talk briefly about what the goals and objectives are for the task force, and also maybe talk a little bit about how the ICG is looking at the private companies that are providing services like Rod talked about.
Okay, can I talk at first?
Yes,
okay.
Please.
Thank you, Jeff. So thank you very much. As I presented in my presentation, CPITF PPP Interoperability Task Force aiming to improve better interoperability between open PPP service. Mainly, it's a government-funded project, but we are also to include some commercial service. I heard in a presentation of TerraStar-X, it's now supporting open format in 3GPP. It's somewhat compatible with our open format. So I think it's very nice opportunity to discuss commercialized service as an interoperable system. And our goal is to better have interoperability of PPP system. And the how to do that is we are currently under discussion. At first we define some common terminology such as convergence time and accuracy, because the many different systems, every system has its own definition of parameters, key parameters. It may confuse the receiver manufacturer or developer. So we must clarify the definition. And then we have intention to define some common model or algorithm, because PPP and PPP-RTK is a kind of new technology. So there are some different kind of modeling. So it may also confuse the developer. So that is our intention. Thank you.
Okay, thank you, Rui. Do either of the other co-chairs want to add anything?
Hi, this is Ignacio speaking. Just from my side, I would like to just mention that we have our second workshop that is taking place in March in JRC ISPRA, and those that are we have members in the task force that are by now aware. But if there are other organizations or people that are working in the domain of PPP, and they would like to be part of the task force, and they can be part of the task force and contribute to the workshop, let us know, and we will pass you all the info. Yeah, just highlight the points by Rui. So the purpose of the group, among others, is to exchange information, first of all. Then Rui in particular has worked on standardizing the formats for providing PPP and RTK. There are some papers on that we have jointly participated to this effort as well. The definitions is another point. Rui already mentioned what is accuracy, what is convergence time, and so on. And then there is a kind of more high level, let's say, more ambitious objective, which is how can different PPP correction services or PPP-RTK interact together in the receiver. There are some technical complications to that related to how you compute the corrections with respect to what, and so on. But this is also an objective of the group, I would say, just to complement the words by Rui that I think already summarized very well what we're doing. Thanks.
Thank you, Ignacio. Okay, I don't know, do we have time for one more question, maybe? If so, maybe a question for Rod. You know, we heard about the different free services being offered by the service providers, and I just you kind of touched on some of the things that you're working on related to automotive, but I'm just curious on your perspective related to sort of industry side of things, and how you see that market shaping up for private companies, given that the other service providers, some of the other service providers are going to be offering services for free.
Okay, so yeah, it's an interesting question. I mean, SBAS is a good example of the original kind of free correction service that people used, but there was if you like, in the background, a safety critical space. There'll be announcements of outages. There'd be that basically that it was being built around an aviation standard that you could use on the ground. Not sure if that's actually yet being proposed for the free services, right? There's discussion going on about the formats and everything else and compatibility, but that still leaves a question mark about the safety critical side. So in an automotive sense, I think the automotive industry is going to drive the requirement. They'll tell you, they themselves are still struggling a little bit with this particular standard, but a number of groups are kind of getting together and they've got a standard already getting a standard together. And in the mobile phone market, it's much more interesting. It's I think free services could be a possibility there because it will be built into the phone and the chip, right? And then large-scale companies may decide to, put as an app for that, and then use the app and use that kind of functionality, where safety critical isn't so much of a problem. So there is a possibility for free services. To join the two together, we of course will be always happy to use your services when they're available. But I think it's still a question about which industry you talk to.